Hey everybody, my name's Mel Strong from the Bradbury Science Museum, and today we're going to make a cloud in a jar. So I'm going to do this here. I want you to follow along at home. You're going to need a few materials. First thing is you're going to need a jar. And it doesn't have, I'm going to use a canning jar. Yours doesn't have to have a tight fitting lid, but you need something to use as a lid, like even a piece of paper will work for this. And then the second thing you're going to need is you're going to need a bag of ice. So these are just some ice cubes out of the freezer. I'm using a quart-sized Ziploc bag. And then you're going to need a match. And I'm going to use some little wooden matches, but you can use paper matches. They work just as well. Okay, so your first step is you're going to put some water in your jar. I'm going to fill mine about a third of the way with warm water. The warmer the water, the better this is going to work. Doesn't need to be scalding hot, but if you can get it warm, that's better. So let me fill my jar and I'll be right back. Okay, so I have put some water in my jar. It's about a third to half full. I'm going to put the lid on it. And again, you don't have to have a tight fitting lid, but put something to form as a lid. And we're going to set that aside and come back to it later. So we're going to be talking about the science of clouds as we go along here. And normally I would ask these questions to my students, but of course you're online, and so I'm going to ask you some questions. I want you to think about this. My first question is, we're trying to make a cloud in the jar. So what is a cloud? Like if you had to describe it to somebody, what would you say? Now, when I ask this to students, I often get the answer that the cloud is made of water vapor. Here's the problem with that answer. Water vapor is actually invisible. You can't see water vapor. But here, this teapot is actually forming a little cloud right here. And it's made out of tiny microscopic droplets of liquid water. That's what you see when you see a cloud. This cloud in the sky here, and these clouds are made of billions of tiny liquid water droplets. All of them are microscopic, right? This is not raindrops. They're much, much, much smaller than that. On the other hand, you can also have some other clouds that look like this. So these are really high up in the atmosphere. These are cirrus clouds, and they have this kind of wispy, hairy appearance to them. And that's because they're made of ice crystals. So this cloud, notice how you can tell there's a sharp boundary between the cloud and the sky. That tells you that the cloud is made of liquid water droplets. On the other hand, if you look at this cloud, you see the fuzziness up here of the boundary. So those of you that have watched my cloud identification video know that this is a cumulonimbus, and we're looking at the anvil, and this is all made of ice. This part down here, where the boundary is very sharp, is liquid. So you get microscopic liquid drops here, microscopic ice crystals up here. We call that a mixed cloud. So my next question is, okay, if most clouds are made of liquid water droplets, then how can we see them? Because water is transparent, so why wouldn't water droplets also be transparent? Well, if you have really, really tiny particles, it doesn't really matter what the particle is made out of. When light hits it, it kind of scatters in all directions, and the result is that something looks white. Which brings up another question. Well then, what's the difference between a cloud that's white and a cloud that's dark? Look at these two clouds. The top of this cloud, the upper part, is white, but the bottom of it is dark. Why is that? Well, this part down here is just in the shadow. It's in the shadow of itself. This part's in the sun, this part's in the shade, right? Same thing over here. This part's in the sun, this part down here is in the shade. There's one additional detail over here, which is that this is rain down here, right? So the rain can often look dark as well. So there's no difference between white clouds and dark clouds, right? It's just if they're in the sun or in the shade. That's it. Okay, let's go back to our jar. Now, you'll notice we've got some little drops on the inside of the jar here. That looks like we're forming condensation, which is not a cloud. But let's first talk about why we are getting what we're getting. So as I've been sitting here yakking to you, there's been two processes that have been going on inside our little jar. There are water molecules that are leaving the liquid, and they're floating around up here in the empty part of the jar. And there's also water molecules that are leaving the empty part of the jar and going back into the liquid. So this happens anytime you have liquid water exposed to the atmosphere. So here I have a jar of water. Now usually what happens is the stream of water molecules leaving is greater than the stream of water molecules coming back. So what happens over time is the level of water goes down and down, and we call that evaporation. All right, well, with our jar, the problem is the stream of water molecules leaving might be greater than the stream coming back, but they can't get out, right? So the number of water molecules inside the empty part of our jar has been increasing and increasing as I've been sitting here talking. Well, it turns out there's a limit as to how many water molecules can stay in the air, and that is controlled by temperature. So the colder the temperature, the less water molecules can stay in a gas. If it gets too cold, they have to condense out and form a liquid drop. If you are in certain parts of the world, you are familiar with this process that we call dew, right? You get up in the morning and you'll notice that there's these drops of liquid on the grass. That liquid was not there the night before. But what happened was, overnight, it was too cold for all of the water molecules that were in the air to exist in the gaseous state, and they condense out and they form these liquid drops. Molecules had to find a place to basically land, and they picked the grass. Why did they pick the grass? Because the grass is really, really thin, and thin things cool quickly. So in the middle of the night, the grass is actually the coldest place. And so that's why the water molecules collect there. Well, in our jar, we got the same thing going on. The water is kind of warm, right? The glass and the lid, which we can't really see, are colder compared to the warm water. So the water molecules are condensing out to form droplets on the inside of the glass and underneath the lid. To form a cloud, it's the same process. Instead of happening here on the surface, we're going to form condensation up in the air. And we're going to do that by cooling the air somehow. If the air gets cold enough, the water molecules cannot stay in the gaseous form, and they start to condense to form these tiny little microscopic water droplets. Now, you yourself may have made one of these clouds. If you live somewhere where it gets cold in the winter, and you can quote-unquote see your breath, what's happening is water molecules are coming out of your body in the gaseous state. They hit the cold air. It's too cold to stay in the gaseous state, so they start to condense out into little tiny microscopic liquid drops, right? You're making a little cloud. Now that cloud is temporary because eventually these little tiny microscopic water droplets, they just evaporate into the air and your little cloud disappears. Also, if you live somewhere cold in the morning when cars are out, you'll notice they are producing little clouds out their exhaust pipes. When you burn fuel, like fossil fuels, hydrocarbons, one of the things that you get out of the exhaust pipe is water vapor. So water vapor is coming out of the exhaust, really high temperatures, hits the cold air, has to condense out, forms these tiny little microscopic droplets. You made a little cloud, and then the cloud dissipates. Coal-fired power plant. If you live near one of these, on a cold morning, you can see clouds coming out of the smokestacks. You're burning coal, water vapor is coming out, it hits the cold air, it condenses into these tiny little microscopic water droplets, and you get a cloud, and then the top of that cloud eventually evaporates into the air. Now, jets often form clouds, and we call these condensation trails. It's burning fuel, hydrocarbons, and so there's water vapor coming out of the exhaust of each engine. And it's coming out at a very high temperature. So there's a gap between the engine and when the cloud forms. The water vapor has to cool down until it starts to condense out and form these clouds. You may notice that on some days you can see condensation trails very well and they stay in the sky a long time. Other days they don't stay in the sky very long at all, and sometimes you can even see jets that don't leave one. And that's completely dependent on something we call relative humidity. The higher the relative humidity, the more likely you are to make condensation trails, and the more likely they are to linger. So here's an example of a satellite image of the southeast, and every one of these streaks you see is a condensation trail. This was a day where it was pretty high relative humidity up at 30,000 feet or wherever those jets are flying, well preserves the condensation trails. Okay, so question then. What we just said is, in order to make a cloud, you got to cool the air until the water molecules condense out to form liquid drops. So, if I take my jar and I put it in the refrigerator, would I get a cloud? Why or why not? The answer is No, you would not get a cloud. Why not? So imagine I put my jar here in the refrigerator. Okay, what's the part that cools down first? Probably the very thin lid, maybe the glass. So what we would see is we would get more condensation, bigger drops, on the inside of the glass and underneath the lid. That's not a cloud, right? In order to make a cloud, we have to cool the air inside of the jar. So the challenge here is what we want to do is we want to cool the air inside of the jar without actually cooling the jar itself. So before I do this, I'm going to explain kind of the process. What I'm going to do is I'm going to remove the lid, and I'm going to replace the lid with my bag of ice. And the idea being that it's going to cool the air right underneath the bag of ice before it gets a chance to cool the glass, and we should form a little cloud underneath there. That's the idea, okay? But before I do that part, we got to talk about one more thing, because there's one more thing that clouds need. When we talked about the dew forming on the grass, the reason it was collecting on the grass is because the grass was the coldest place, but also the water molecules need a surface. They need a surface to condense on, and they need a surface up in the cloud as well. And the surface up in the cloud is little tiny, tiny, tiny particles, mostly of dust. And we call these things cloud condensation nuclei. So if you could look at these things under a microscope, here's some examples of what cloud condensation nuclei look like. These here are all different versions of dust, and the kind of dust you have depends on where you live. A lot of places have a lot of salt in the air, and the salt crystals occur because in ocean waves smash together, it makes mist that goes in the air. That ocean water evaporates and makes little tiny salt crystals that they float away into the air. If you live near a coal-fired power plant, you might have a lot of what we call fly ash in the air, these tiny little spheres. If you live in a city or near one, you may have a lot of these spheres that are the result of burning diesel fuel. Little tiny little black spheres floating around. Even something like bacteria can get blown in the wind, and pollen's another good one. So there's a lot of different things, but we need to have some little particles in our air to form clouds. So for our jar cloud, we need particles, right? And so this is where the match comes in. So again, I'm going to explain this before I do it. What I'm going to do is I'm going to light a match, I'm going to blow it out, I'm going to open the lid, I'm going to throw it in, and I'm going to replace it with the ice. And this all has to happen like pretty rapidly. Once I do that, the cloud should start to form in here within like 30 to 60 seconds or so. So it's kind of a short time frame to do this. So for mine, I'm going to get it ready and get my match. Get my ice. Okay, so try to do this without setting my cat on fire. Throw it in, replace it with ice. Okay, now, I don't know if you can see that, but I'm getting a cloud forming inside my jar. And one of the things that helps is if you have a black background, like a black wall or black paper or anything like that. But I'm forming a cloud in my jar. Now, what I'm going to do is I'm going to lift off my bag of ice. I'm going to let the cloud out the top. So as I do this, watch at the very top of the jar for some of the cloud to escape. And there it is. Okay, so I'm going to make a cloud in a couple different ways now. The one I just did, you can do at home. These next two, probably not. For the next one, I'm going to make a much more impressive cloud, because what I'm going to do is I'm going to make the air much colder than I did with the bag of ice. So for this first one, I'm going to use dry ice. So you may have done this before, or maybe you've seen it done before around Halloween or something, where you just take dry ice and you put it in water, and immediately you get this big reaction, it looks like. Well, you're just making a cloud. So if you've seen this before, great. But let's explain now what's actually happening. So here I've got some dry ice, and I've got a little just jar of water, same jar, same water. I'm going to put the dry ice in. Okay, so again, the classic dry ice and water makes a cloud kind of thing. But what exactly is happening? Now that we've kind of explained how a cloud forms, can we explain this? So the purpose of the dry ice, so dry ice is just frozen carbon dioxide. It's really cold. It's like, I don't know, minus 100 or something like that. And as this thing is in the water, it is releasing cold carbon dioxide gas, which then bubbles up and mixes with the air that's in here. So the only thing that dry ice is doing, the reason this works, is because it is acting as an agent to cool the air that's inside here, right? So the dry ice is not making the cloud. The dry ice is making the cold. The cold is making the cloud. So what we see in here is we see little tiny microscopic liquid water droplets that are forming a cloud. And the reason the cloud exists is because the temperature inside the jar is too cold and the water droplets are going from the vapor state to the liquid state. Okay, so far what we've said is in order to make a cloud, you need to cool the air down until condensation occurs. But we haven't really explained why that happens or when that happens in nature. So usually the reason that air cools down is because air is uplifted. There's some event that makes air rise, and when air rises, it expands. And the reason it expands is because as you go up into the atmosphere, the pressure decreases. So if I take a bubble of air and I make it rise, it's going to expand, and as it expands, it cools. That's due to what we call the gas laws. So for example, here in this time lapse, you see that there's air rising, and the reason it's rising is because there's little plumes of air warmer than the air around it, and as it rises, it is expanding, and then eventually it hits a point where condensation occurs, and that's where you can actually see the clouds start to form. And it continues to rise as long as the plume is warmer than the air around it. Okay, so this last way I'm going to make a cloud is one that you can't really do at home because it requires some special stuff. But what I have is I have a 2-liter bottle, and what I've done is I have put in some isopropyl alcohol. It's actually pretty close to pure isopropyl, 99%, and I just put a teaspoon of it in here. And it's been sitting in here for a little while, and as it's been sitting, it's kind of been evaporating, and inside now is a lot of isopropyl molecules floating around in here in a similar way that we had with water. Okay, well, one thing I can do with this is I can pump it up. I can pressurize it. So this little ball on the end here is pressurizing the air that's inside. So as I'm pumping it, the air pressure inside is increasing. Okay, so what I've done here is I've just increased the pressure inside the bottle. So as I was pumping this, the pressure inside increased, and when you increase pressure in a contained vessel, the temperature goes up. So this actually feels a little bit warm to me right now. Okay, now that part really doesn't have anything to do with nature, but what does is what I'm going to do next. Because what I'm going to do next is I'm going to release the pressure inside here. So in one instant, the high pressure inside this tube is going to suddenly decrease, and the air is going to expand out the end of the tube. As it expands, it cools. And as it cools, it reaches the condensation point for the isopropyl alcohol that's inside. Okay, I'm going to release the pressure in 3, 2, 1. And there we have a cloud of isopropyl alcohol. And we got this by cooling the air through expansion.